Thanks a lot. Actually, I'm very happy to speak last. And the reason for that is it gives me time as I prepare my talk to sort of prepare my talk for you, actually, and tailor my comments to the kind of things that have been going on all week. And so I'm going to extemporize a little bit in the beginning and just give you some context about what I'm going to say, but also at least from a perspective of somebody who does numerical and scientific computing, what went on or what has been going on. And, you know, domain decomposition is kind of an important thing in scientific computing. It's been around for a long time. And, you know, this picture now that's embedded in my brain of, here and then here and here, this is compact diffuse bulk, right? And, if some person walked into one of the lectures and looked at the slides that somebody was presenting and they were numerical, they said, oh, what's going on here is people are using domain decomposition to solve multiphysics problems, okay? Because that's what we've been talking about, is thinking, and domain decomposition means exactly that. If you have a physical domain, you break it up into different regions, and you have different models for the different regions, and you couple them together. And what we've been doing is, of course, has been having people that talk about what goes on in the different regions, okay? And sort of one of the motivations for this whole workshop is, I could describe not only boundary conditions, because that's one way to couple them together, is just keep them distinct, but just in general, how do you combine solutions over multiple domains, especially if they have multiple different types of models. And as I mentioned, domain decomposition has been around quite a while. I remember as a graduate student, somebody told me how to, showed an example of doing this to compute airflow over Boeing 747 or something. And I just went, wow, that's just amazing that they can couple all these domains, and they had lots of computers that could exploit parallel computation. So if somebody said, well, why are they still talking about it if it's been around since, a long time? And I think one of the reasons is the models in here are really complicated. And not only that, they have stochasticity, okay? And that's a little different, I think, than at least my impression, since I've been paying too much attention, but just in general, I think people that think about domain decomposition from a numerical point of view, you basically have deterministic equations. And so there are these challenges now of sort of combining different models in different domains, especially when the models have stochasticity, okay? Now, that said, what am I up here talking about when I could, since I told you that this is a topic which has been around for a while, and I could have somebody asked me, well, what should we do? I'd say, well, just go Google domain decomposition plus multi-level physics, and you get lots and lots of papers. There are a lot of ideas that people already had about how to combine multi-physics solutions, okay, from a sort of a computational perspective. So why didn't I do that, or why didn't I agree to come? Because there's a way of coupling multi-physics simulations, or just coupling domain decomposition models and domain decomposition, which doesn't sort of stand out if you do that type of search. And that's what I'm going to talk about. It's a different way of using domain decomposition to put them together. Now, what's interesting is that this sort of alternate approach, which isn't really talked about, is actually the approach, I guess, that Jorg started many years ago about adding charges, a very physical-based approach for doing things that couple these solutions. And what I find really neat is that sort of I come at things from a PDE perspective, and Jorg and his colleagues, and probably most of the people in this audience do, is from a very physical perspective. And there's a unification, I think, that they are actually the same thing. And that's what I kind of hope to get across to you and show why the perspective PDE thing might be useful. But at the same time, understanding this maybe makes you realize that if you went out and did a search for domain decomposition and multi-level physics, why the way they're doing things doesn't look like the way you're doing things, because you're doing it not the sort of the standard way that's evolved over time for combining multi-level models. Now, that doesn't mean that the other way that's been done for quite a few years is not important. There may be really good ideas, and I would recommend people go out and actually Google multi-physics plus domain decomposition, because if you want alternate ways of combining solutions, there are a lot of ways that have been produced. Okay, that said, I'm going to be talking about using domain decomposition to couple solutions, more like you guys do already, but from a PDE perspective. Now, there's a bit of a problem, and that is that I don't study electrochemical cells, okay? So I'm going to have to describe it in the context of the type of problems that I've been working on for the last 20 years, which is semiconductor-based quantum devices. Now, you might think, wait, so this has nothing to do with electrochemical cells, but what I hope to convince you is actually sort of from a mathematical perspective, if you kind of blur your vision, we're doing a lot of the same computational tasks. And so what I'm going to be doing here is I'm going to give you a little bit of background about semiconductor-based quantum dot devices, draw some pictures, and then draw another picture so you see the pictures look the same. And then I'll talk about the method, and I'll show how the method works in the context of semiconductor-based quantum devices. And then, because I've been sitting here and getting ideas and talking to other people, I'll also outline what I think may be a path forward to actually improving some of the accuracy with which certain types of boundary conditions occur when you want to do electrochemical cell modeling. Okay, so let me begin. So this is mostly just sort of prelude to the story. I'm associated with the CQSE Modeling Simulation Group. That's the Center for Quantum Science and Engineering. What are our objectives? We're supposed to create simulation tools for people making semiconductor-based quantum dots. So what, people that know about Google and quantum devices, they know they make superconducting quantum dots. What's interesting in that and semiconductor-based quantum dots. So this is transistor technology. So these are a lot smaller. And the whole idea, why did people do this? Because they want to take advantage of 80 years of experience making transistors to make quantum dot devices. Here's the group that I work with. The reason I'm showing the people first is because I just want to point out that everyone but this one, me, are physicists. And the reason I'm pointing that out is because this gives you an idea about what the type of work that goes on in our group is. And that's primarily looking into the physics. Okay, so even though it says, creating simulation tools, there's a lot of model development in it, and that's what's going on now. Because what we're capitalizing on is for the last 20 years, developing the simulation components, but now there is this thing about what are the right models to use, which models can you use that are sufficiently accurate for answering the questions that the experimentalists that we work with get along. Okay, so that's the group. And what do I mean by simulation tools? Well, I'm showing a picture which is just like everybody else's picture. You got atoms and device scales, and then we also have device scale simulation, which actually means ODEs and things. So, there's, in these devices, there's certainly atomistic scale modeling that's needed because they're made out of semiconductors. There's device scale modeling, so what happens when you put on gates and how things work. And then, of course, there's, that's too complicated. If they actually want to make a device with hundreds of thousands of gates, you have to develop sort of an ODE model, which, basically a circuit model, which then allows people to think about control dynamics and error correction and all that kind of stuff that you need to do to make a quantum device work. Now, we don't do all of that. We only do the stuff in the middle. But we do have projects where we collaborate people doing atomistic scale modeling to answer questions that come up when that type of modeling is needed to answer questions about what goes on in the device. Similarly, we work with people who work with these effective models. We help them parameterize them based on physical quantities. Okay, so what's a silicon quantum dot device look like? Well, basically it's a I could use the pointer. Turn it on. Whoa. There. That was the erase button. Here we go. We got a layered semiconductor material, oxide on top, some silicon oxide, a bunch of stuff, a buffer layer, and then here this sort of green bar here is strained silicon, and because it's strained, it has kind of a crystal structure, and the electrons like to be there, which means it has a band shift, and down here's another buffer. So the idea is you have this vertical structure, and there's electrons. The electrons have an affinity to be within a quantum well that's defined by this strained silicon layer, quantum well. Okay, so they're confined vertically. Electronic charge is confined vertically in this device, and then it's confined laterally by imposing potentials using gates on the surface. So this is what a gated surface looks like. And where do the electrons come from that are going to be isolated underneath the gates to make quantum dots? They come from these reservoirs on the side, and these sort of yellow boxes are ohmic contacts. So basically you pump electrons in here, and they're able to flow across and then occupy distinct locations in the device. Here's what the structure of the device looks like. Here's the quantum well, and this is where they sit down from the top. Okay, so this is basically the quantum device, and the game that's played, at least that I need to play, is that how do you place the gates? What kind of materials? Where do you place the layers? In such a way that you can actually capture isolated electrons inside the device. And moreover, can you modulate the gate biases to introduce certain types of electronic interaction between those isolated dots so that you could basically get a hold of a subspace of electronic states, electronic structure states, so that you could store quantum information and do quantum operations. Fine. What are the simulation models that are used? Well, we're using the M-particle Schrödinger's equation, but we're using the effective mass approximation. So this is sort of a continuous approach. There's no resolving of atomic features. I now know I should call it implicit metal, I guess, which just basically means it's metal with a dielectric constant. These things are very cold, so they're operated at a few millikelvin. So they're basically things are frozen in. And what does this mean for the electronic structure calculations to do? Because we're using the envelope function, it doesn't resolve the atomic scale fluctuations. It's basically the envelope of them. Typical sizes, if you have gates about 40 nanometers, a single electron wave function. The maximal size is about 40 nanometers, typically a lot less, 10 to 20 nanometers. But of course, atomic spacing is about 1/2 nanometer. So these are, we're solving Schrödinger's equation, but we're not resolving the atomic scale features. And here's just a picture of lots of dice, and here's the charge density. These are the electrons that have been trapped. There's more electrons down here. This forms what are called sensing dots. They go forward. Okay, so that's the simulation model. And just to say that there's some reality behind this. So there's a code called mask MDMM, which is our core simulation code. MDMM stands for multi-domain, multi-models. And we use domain decomposition quite heavily, not only in the vertical direction, as I'll talk about, but also in the lateral direction. So in these devices, you have to separate different types of models depending on where the charge is accumulating. So these big blue regions, basically we do not do a full quantum mechanical calculation. We do basically a Thomas Fermi type thing. It is quantized in the vertical direction because you have to be located there, but you can basically get, charge, given a potential, you can determine a charge density here, which is quite accurate actually. On the other hand, when it comes down to controlling the states and the quantum dots, you actually have to do a very, very refined calculation. In particular, you can't use DFT, we have to go to full FCI. So we're actually solving Schrödinger's equation for few electrons in these regions, and because we don't have nuclear potentials, there could be arbitrary, we have to use potential-dependent orbitals. So anytime you have a gate bias, you determine a potential, you determine a set of orbitals, and then you do FCI. And that's been honed over the years, and in fact, I probably talked about it at previous IPAM meetings about how that works. Okay, so now I'm going to leave this. This is sort of the context where we're doing things. I want to get along to the thing that is related to what's going on here. So what is the computational workflow? Well, it's what you'd expect. You have an electrostatic potential in the device, and you have to compute it. You have the quantum region, and then you solve Schrödinger's equation. You figure out what the charge is, and then you repeat. So you just create self-consistent solutions. Okay, so this is the typical self-consistent Schrödinger Poisson calculation, although we're introducing different models for the way we actually do the population. We actually use full FCI in the dots, and then this other Thomas Fermi type approach for the outside. One of the challenges of this particular task of doing these solvents is that the energy level differences of significance are about 10 microeV. That's because we're very cold, and we're interested in the difference between ground and excited states of these things, and they're very close together. So it's not 1 kcal per mole, it's a lot less. Okay, and it's 10 microeV by O of 1 gate bias. So the idea is you want to wiggle these things a little bit and cause the exchange energy between the dots to change. So what's needed here in terms of just the potential calculation is something that's very efficient, and in particular, low numerical noise. This is very important, because the thing is that any sort of noise that's introduced by an iterative process or whatever contaminates the energy level things that you're trying to observe. Okay, how does this relate to electrochemical cells? Well, when I saw this picture kind of on its side, because I think Jorg did it at the tutorial, this is compact region, fused region, bulk region, and then you have the metal. Well, actually the sizes here, the lateral sizes aren't the same, but actually the compact region is about the same size as a quantum well. It's a bit, I'm actually larger. It's a nanometer or something like that, 2 nanometers for the compact region. So we have the smallest quantum well we have is about 3 nanometers. You run into trouble if it's smaller, but this is what it looks like. And what do you have? How do you do the simulation? Well, you have to do electrostatics, chemical potentials. There's an additional wrinkle. I must say you have much more complicated physics, at least to me. And then you get charge density, and there is this overall self-consistency loop between the things. Very simplified, but it does point out that you do need electrostatic potentials. It's part of the component. Okay, so in some sense, domain decomposition, you want to do different things, and somehow it should apply. Okay, so what is the challenge with the kind of devices that we work? Well, that particular code I mentioned, run MDMM, is optimized for applying gate biases just on a planar surface, because that's simple. And if you don't really care about gate structure, just what is the potential they induce, that's fine. And moreover, then it reduces to doing calculations in a box. And you can do calculations in a box very fast with fast Fourier transforms. Okay, so that we have a very fast solver for that. Trouble is, people come along and say, well, actually, now we want to understand what the effect of those gates is. That's a problem, because first of all, when you start doing three-dimensional gate geometry with bizarre dielectric coefficients or who knows what, you then are talking about finite element solutions and in 3D, and it just takes a while to solve 3D electrostatics problems with complicated geometry. So the concept is what you would like is to replace that whole, everything that goes on up here in this complicated region by a planar surface, some sort of boundary condition, which you can then just couple to the fast Poisson solver that goes on down here. Now, it has to be parameterized because whatever you put there, there's a dependency of the solution down here on the gate biases. That's why they work. So somehow you have to incorporate into your interface boundary condition, your boundary condition, that parametrically what the gate biases are. So now what I want to delve into is how do you derive that boundary condition? Okay, so here's the story. You have two regions, and you want to do some work and come up with a parameterized effective boundary conditions. So the way I'm going to do it is I'm going to go through the lens of domain decomposition, sort of the classical stuff. So now I'm going to do a little background in domain decomposition for Poisson's equation. If you went to a talk that a numerical analysis is about domain decomposition, they basically show you this sequence of pictures, at least in the beginning. Okay. So first of all, they'd explain what is the idea behind domain decomposition? Well, let's think about Poisson's equation. I got a region, and I break it up into two pieces, and I have a solver for each region. I can solve it, say, quickly in each region for whatever reason. And the game is, how can I use solvers in each of these regions, combine them to get the solver of the whole domain? Okay, and that's the question that domain decomposition, when people talk about it from numerical viewpoint, answers. Okay, so there's an observation that's made, and it's pretty straightforward, which is that if you happen to know the solution on the interface, then you're done, because for Poisson's equation, it's completely determined by the right-hand side and the boundary values. Okay, so if I know the values here along the red, and I solve it in A, and given those values, I can solve it in A and solve it in B, and if these are the true solution values, then they will match up, and I will get the solution over the whole domain. Right. Okay, so what's classic domain decomposition? I alluded to this sort of historical way that people have been using this technique, and they've used it on Poisson's equation. And in fact, it was started by Schwarz in 1870, nice paper in German, talking about how to do this process. It's kind of amazing. But if you go out on the web, you'll see that they all kind of have this pattern that they say, okay, I have these two solvers. How do I combine the solution? They say, well, do something in A for a while, and then evaluate the boundary values, and then solve it in B for a while, and then get the boundary values, and then do A. So there's this iterative process where you're consecutively applying one and then the other operator, okay? And then ideally in the limit, what happens when you sort of do this alternating thing, that's why it's called alternating, you end up with the values on the interface, and then you can fill in both sides, okay? And this is an interesting idea, and so math people got a hold of it, and linear algebra people got a hold of it, and so what have they been thinking about? Well, first of all, what governs the convergence of this process? I mean, they ask these kind of questions, or given that it is convergent, how could you accelerate it? That's the whole concept, that once you have sort of a technique, how do you make it go faster? How do you prove it works? Doesn't always work. You have to choose different things. Here I've had a simple case with two blocks, but what happens if I'm trying to put this on a 64 thing? So suppose I break up the domain into 64 8x8 blocks. How do you make all that work? Okay, so you'll see these kind of papers. Now the thing is, that doesn't really help in terms of this kind of thing, because the whole idea is that you don't want to have to solve them over and over and over again, right? That gets too expensive. So this sort of self-consistency that you do use in the classical domain decomposition doesn't work for us. Okay, so there's another way to do it, which has already been discovered, but from a PDE viewpoint. What's the idea? Well, the idea is that if the solution on the interface determines the solution, fine, just write an equation for the interfacial values and then solve it. So do that first, and then solve on either side, okay? So then the question, to get started here, you have to have an equation. So how do you get the equation? So I'm going to talk about sort of obtaining the equation sort of through a quote-unquote derivation from a continuous viewpoint, and this is important so we can use analytical models if we want. But there is a way to derive equations for interfacial values between these two regions from linear algebra viewpoint. And I'm just mentioning here, if you look at the slides, because if you have a complete discretization over the whole domain, and you isolate the unknowns along the interface and structure your matrix appropriately, you can find equations for the interface that you can solve first, and then you solve the equations on either side. And that set of equations is known as the Schur complement. Now, you don't even have to be fancy linear algebra. Usually when I teach it, I just say, look, you're just doing block gas elimination. So gas elimination says, do something to get down to the corner, and then you work your way backwards. Okay, so this is block gas elimination, but you're using, instead of numbers, you're using matrices. But same idea works. So there is a way, if you have a discretization, that you can write down the equation for this first and then combine them. Now, this isn't too useful for what we're doing because we don't want to start with a discretization. What we want to do is start with just a generic model. So when you're driving equations, what you do is you say, well, what has to be satisfied? So physically, what has to be satisfied is you need continuity across the interface. You need that whatever you put here, you're going to use the same value when you're solving this as when you're solving that equation. So that's continuity across the interface. And then the other thing, this nice thing about elliptic problems, is that it's sufficient to get a whole solution to also just include that you have continuity of the normal derivatives. Okay, so there's a minus sign here because I'm assuming one normal derivative. I'm just picking one direction. I want the jump in the flux across the interface to be equal to 0. Okay, so how do you get the equation? You just think about it. You say, okay, fine, I'm going to develop the model which says take any values on the interface and then figure out the operator that maps it to the fluxes and then set that, set the flux on either side equal to 0. So that's the way you drive the equations. It's just a flux balance equation. So sort of semi-formally, here I have the flux balance equation, and in words, the flux in solution A due to the boundary values, the right-hand side, and the boundary values that are not on the interface has to equal the flux down here on the B side, around the edges, and in the middle, or introducing some notation, and by linearity, you can express it this way. So there's a linear operator that says take the values on the boundary, figure out the self-induced flux there, and then you've got some flux due to the right-hand side, and the forcing has to equal the flux, self-induced flux on the B side, I guess down here, and then the flux that way. Okay, so you can do this sort of formally. And the nice thing is that these are linear operators, which means that if you pick a basis for the values on the interface, they're matrices. Okay, so you can set up a matrix equation, mx equals b, and you can construct this in advance. You can find LA and LB, and then you've got the right-hand side, which depends on fluxes. Okay. So what do? So how do you use these? Well, you have your system, you pre-compute the entries in these matrices, and you also parameterize the right-hand side forcing that's due to the A part. So this works for us because we have some collection of gates. When you push on one gate, keeping all the others 0, you can figure out how much flux it induces. And so that generates a vector. And then you do that for all of them, and it's a linear problem. So in some sense, the flux induced by this collection of gate biases can be expressed as a sum over individual vectors of values on the interface. Okay, so you can pre-compute these things. This just depends only on the structure. And then given the density and boundary values and the upper domain parameters, suppose you want to actually solve a problem where you're doing stuff down below, you basically determine the interface values by solving this equation. Okay, so you use pre-computed information, and it kind of goes like this. The steps are, 1, you have to compute the flux that's due to the stuff down below. Well, that's a B solve. You just have to solve it down there, evaluate the normal derivatives, that gives you the flux. You then have to accumulate the forcing due to the top. Well, that's just the linear combination of stuff you've pre-computed. And then you have to solve a matrix equation, but the entries of the matrix have been pre-computed, so you just have to solve it. And then once you have the boundary values, you can just solve on the bottom. So why go to all this trouble? Because the thing to note is that if you're only interested in the solution in the bottom, you don't have to do any solves up top. You're encoding all the information about what's the electrostatic interaction of the top with the bottom through this equation and the matrix coefficients in L sub A. Okay, so that's basically the strategy. How does this work out in silicon-based quantum devices? Well, okay, so we have a situation where we've got complicated geometry up top, or, turns out, you can also have an upper domain which is infinite. Okay, you can glue on an infinite domain block, figure out the Dirichlet-Neumann map, that's his map boundary values, analytically, actually. It's diagonalized by the discrete, by Fourier transform, or actually Fourier series. So given these things, you can calculate those operators. So you either do it, because they're linear, you can just send through a basis and get them column by column, or as I said, you could do it analytically. You can also just calculate the forcing that's due to gate biases and things by just putting in unit gate biases and then evaluating the flux they induce. And then given these values, you can set up equations and solve it down below, like I said. Now, before I give an example of this, there's an interesting thing you can do with the data you collect in these operators, is that if you sort of collect data on both sides for these things, you can then combine three of them. This is just an offline calculation separately done. You can then combine them to a single boundary condition. And I mentioned this one, you can connect things to the infinite. This is just not working well. The infinite case, now what's going on here, this is a representation of a STM tip, and this arrow means that you can actually parameterize its motion. Now, the way that the parameterized motion of this tip was done was not to regrid it every time you moved it, but to create the map, the data that you need for the Dirichlet norm, to construct the boundary condition. And because if it's in a periodic domain, you can just multiply phase factors. So you can move this data instead of moving the tip, and that should be quite useful. Okay, and then you can glue on the gate biases. Now, why did I show you this picture? Because this is how we did this problem. So, and this is sort of the demonstration of kind of what it's good for and some of its properties. So I work with experimentalists, and STM tips, as Stefan was already working with, you can use them for interesting things. They were using it for something non-interesting. They're just using it as a source of potential. So let's just put a potential, and then they actually have a way of actually putting in a tank circuit and detecting things. So they're using this tip as a moving gate, which they can do some, I guess, reflectometry, who knows what, but they're able to actually sense things. And so they had this great idea that maybe we could use it to basically interrogate what the structure is of the quantum well as felt by an electron that might form a quantum dot. Okay, so one of the difficulties in these devices is that things don't always work. They get weird noise sources and stuff varies as it moves around or depending on where they pattern the gates. And you'd like to be able to know, what's causing it. And so you'd like some way of interrogating what's going on in that quantum well. And they have been slicing it and doing bang, whatever X-rays and who knows what to figure this stuff out. But the trouble is, you've got to hit the right place. Okay, so it would be really neat if you could just have some way of figuring out what's going on inside this quantum well. And not just at the atomic scale, there's not enough resolution. These things are very big compared to the atomic scale sensing, so it's not a way of doing atomic scale resolution, but what you can tell is what would be the influence of atomic structure on a dot. Okay, so you're actually trying to capture the thing you really want to know is how does atomic structure influence what goes on here? So the instance, what happens when you have a step, right? Or alloy disorder or various other things. Okay, so this is the idea, and so this was coded up and basically using these pieces of a model for the tip and the gates, and then it was moved around. And the results are written up. I think the operant word is towards, because they did this and they're okay, we got to change the design. I mean, it's actually hard to build these things. Okay, but the idea is that the reason we got involved is because before they spent a lot of time trying to actually make this thing happen, they want there's some fundamental questions that have to be asked. In fact, the first one I asked was, how do you know you can get a single electron here? It's actually, these things are hard. I mean, the point is that you've got a reservoir over here, and yeah, it's easy to pull out a bunch of charge, but you want to pull out just one. Is it even possible to do that? Do you have enough control? And secondly, even after you have it out here and you start dragging it across, can you do it adiabatically? Oh, that sounds to be a challenge, because this potential that the electron sees is not uniform by any means. It's kind of crazy because it's shaped by the potentials on the gates. Okay, so what are the results? Yes, you can get a single electron, but it requires sort of thinking hard about how to do the gate biasing and the tip biasing depending on where the electron is. So in the first case, you bias things so you have a reservoir, that's that red underneath the part, you get basically a dot, Jason calls them tweezers, and then you turn off all the reservoirs, you force the stuff to go out to the sides, then you have to move it away from the dot. Now, it looks like nothing's really changing, but it is changing because if you don't bias the tip appropriately, it'll basically want to go back under the gates. So this is one of the problems, you have to sort of reverse tunneling you have to worry about in this level. And what you're seeing down below are the biases of the varying gates, et cetera. and you have to do a little bit more, and then finally you can get it out into the open, ungated surface. And then what you're seeing here is how you have to bias the tip to drag it adiabatically across, the surface, basically out in this direction. And you're modulating a tip that's about 26 volts, okay, which seems to be not unreasonable for what they were thinking about. Okay, so this is useful. Why did we have to go to the trouble of using these boundary conditions? Well, when this thing moves, you really want to avoid having to regrid everything. This would have been a real pain in the neck, because this is geometry moving relative to each other. And what's nice about the effect of boundary conditions is that this tip was for a block where I could translate it analytically and then create new boundary conditions that reflected the fact that I moved it. Okay, so how good is it? Well, one measure is like, okay, let's see if we can bias things to get adiabatic translation. And the first thing you try is, well, maybe it doesn't really matter. So what you decide is, well, you kind of look at the potential and say, okay, fine, it's sort of going up, so maybe I should keep on pushing down. So you just choose a linear voltage change as you move from point A to point B, where you increase the potential. And so this is what it looks like. And what you're seeing here is the ground state and the first two excited states. And you get, okay, well, it goes Fermi level 0. Unfortunately, it kind of goes down and then goes up again. I think the way I figured out the linear thing was I said, okay, at 250, I want it also to be 0, so I'll just figure out the line of the potential that basically would compensate that. And you see, well, this doesn't work too well. Okay, so then what you have to do is, okay, fine, how am I going to figure out those potential values? Well, you can hook this up to a root finder. And for every position, you can say, how should I bias the tip to get basically an energy that's few 1.5 or 1.47 millielectron volts below Fermi level, and then you move it across. Okay, so this is what the electron energies look like as you go across. And then instead of a 10 millielectron volt evolution, you can get 0.01 micro EV. Okay, now you may think, well, why do you really need this small variation as you go across? Because maybe you're looking for a signal, which is variations about that, a smooth signal. That's true. On the other hand, this turned out to be a nice demonstration about the accuracy which is possible with the simulation, because here we actually are able to capture an avoided crossing, which is really difficult to see here, but it's actually here. And you may wonder, is this a bug in the code? Why is it that when you're dragging it across, you see this? And it has to do with the fact that the dot is slightly elliptical when it's near the gates, and as you go this way, it becomes circular. Okay, so there's a degeneracy, and then it becomes slightly ellipsoidal in the other direction. And so this transition in the second and third, first and second, if you count 0 as the first one, second and third excited states, that's this avoided crossing that's happening. And it's able to resolve that. And you may think, well, who cares? Well, they care, because it turns out these kind of energy avoided crossings, these are important for quantum mechanical operation, because if you have to worry about singlet triplet splitting, that's very small. Okay, so this was not only a demonstration that you can create a way of computing the potentials that's very nice in terms of being able to move stuff around, shuttle dots around, but it has a requisite accuracy. Okay, so let me just point out some useful features of these type of boundary conditions.
Can I ask a quick question?
Yep.
So these avoided crossing, are they using that also because these are stable points and they can do things like clock transitions? Is those terms in your team?
This is becoming important as they actually try to shuttle electrons from one place to the other. And what you want to make sure is that states don't get contaminated. So if you had an excited state for some reason and you're dragging it across, it's going to mess things up. I mean, that's my understanding. Okay, so how they actually incorporate it, I don't know. I mean, there are people. So what this does, it means that it would allow you actually to think about how should you bias gates in such a way that as you move it, you keep a separation between those two excited states. I mean, in general, basically, you try to keep as much separations as possible between all the states.
Okay.
And this is just an...
Using transitions between those states, maybe coupled to some electromagnetic pulses or so.
Well, not yet. They aren't doing, I guess you're talking about DAPS, is that the right?
Yeah, little gaps. These avoided crossing.
I'm saying DAPS, DAPS, digital something, pulse, something spectra. I mean, we should, I said towards, and the reason for that is two things. They have to think really hard about how to make the tip, and secondly, they don't want to use this geometry. They're thinking of different structures now to use the same technique. And it involves doing exactly what you're talking about, which is trying to figure out as you transition up and back whether or not these splittings are, can actually detect things that are going on locally. Yeah. Yeah. Right. Okay. So sort of a numerical perception. So what are okay? This is a cool thing and got some results for a problem you don't even care about. That's fine. But I want to point out, there's some nice features of this, and that is that, well, first of all, there's some computational efficiency because we can use the solver down below. But there's kind of a neat thing going on here, which isn't completely described here. But for example, what's going on here is some complicated electrostatic stuff happening because of this. And all of that goes away and encapsulated into a single boundary condition. And that's kind of a neat thing. And actually, this is exploited here because there's this fact that suppose I did an iterative solver to get the data. It can be noisy. That's fine. What's going to happen is that some of the coefficients aren't going to be particularly accurate. But when you use that data inside the simulation, all that noise is gone. Okay, I may have the wrong values, but they aren't going to fluctuate with what goes on up here. Okay, so there's this sort of neat thing that encapsulating the sort of the effect of this inside this boundary condition reduces noise. Okay, or, well, as I'll explain in a minute, if this has true noise, you're going to get an accurate representation that hopefully isn't contaminated by the numerical stuff. Okay, and then, as mentioned, that when you couple this thing, you end up getting a fast direct solver, which means the variation of what's going on here with respect to all the parameters, the gate buys, et cetera, is extremely smooth. Again, if you've ever done numerical work and had to deal with iterative processes, if you want to make sure the fluctuations in numerical work, oftentimes that means like 10 to the minus, well, we have to go to 10 to the minus 10 in precision in the energy level, so that means the potential calculation has to be very accurate. Turns out that goes away. If you have a direct solve, fine, you just do it and you get machine precision, so you get a few more digits. Okay, so this turns out to be incredibly useful for that type of simulation, doing other things when you're trying to muck around with these quantum states. Okay. Right, so how does this possibly apply to what we're doing here? And so, these thoughts came about because I was thinking about, well, I'm going to talk about this stuff. And somebody can ask, well, who cares for what we're doing? So thinking about, okay, how does this interact with what we're doing? And there's kind of a neat thing going on here is that actually what's going on here in the way of deriving these boundary conditions, it doesn't matter what you do in this region. You can have any process you want that's mucking around with the potential, any distribution, the charge density, I mean, as long as it's an electrostatic interaction, that goes away because all you need to know is what its normal flux is that it induces. Okay, so you could have polarized things, solvated things, multiple, it doesn't matter. All that will get washed out in what goes on down here. I mean, the data you get down here will be different, but in point, the differences go on, basically get washed out. Okay, and then the idea is down here, if you're doing something realistic, this is where you still do the computation. You still have to do things down here, but the coupling here is determined here. So how might this work? Well, you use an effect of boundary conditions. So if I were doing it, here's the equation. What you have to do to use this is, first of all, you'll need to compute the flux. Well, first of all, the implementation is a little different than most people think. They think, oh, an effect of boundary condition, I just do something here and solve down here. No, there's a two-step process. You have to do something here to get the contribution to the boundary condition. That's this part. And then you have to figure out parametrically what the contribution to the top is. And then you have to solve an equation to get the boundary values. So it turns out in this case, these operators are known. They're diagonalized by the discrete Fourier series. Okay, you can actually figure out what these operators are diagonal in a Fourier basis. So in some sense, this part is trivial. This part is what it is when you use whatever method down below to calculate the charge density and figure out its electrostatic potential. And then there's this part, okay? Well, if you give me a simulation, I can, basically collect this function as the time evolves. Okay, so that doesn't sort of help though in doing time evolution. So the point is, there is a way to gather the information you need to put here to use the boundary condition so everything works out from PDE, theory, okay? So that's done. And yesterday afternoon, I sort of put things together and said, oh yeah, okay. Oh, and by the way, I should say that when you figure out the values that get put up here, the constant term is what you would do based on what you org, and I guess you talked about higher order corrections. The thing is you can basically create corrections to all Fourier modes. So basically everything done down here. So that part's good. But the hard part here, so that's a utility of this approach, is that you can extend that accuracy. But I was stumped here. I said, fine, so what?
Can I ask
Yeah.
something?
Yeah, sure.
I mean, that boundary between omega B and omega A,
Yep.
I mean, should be in a region where, let's say, the bulk conditions for omega E are reached, so that the exchange, can happen, and then you can measure the stationary flux in or out of the quantity, or it can be even before that is reached.
Well, okay, so you can put it wherever you want. The influence on the accuracy will be changed. So I should say it's not the flux of the material. This is the potential flux, so it's the normal derivative, okay? And in 1 second, I'll say the answer good. So the answer is, how do you do this? And so there's complications, okay? So fortunately, I ran this by Stefan, and he said, oh, yeah, I know how to use this information to create a stochastic boundary condition that you would use here that preserves statistics. Ooh, it's got a tingly, right? There's this interesting thing that, oh, this is what he thinks about. This is really cool. Okay, so he has a way of figuring out what to put here based on the information you gather here, say over some epoch, so that this way of doing the boundary conditions, you would solve down here, get this, put in the stochastic forcing, solve this equation, get phi A, and then recompute. Then you have a model. Okay. I don't know if it worked. He had to run off because he has to go back to Germany. But he has a way of expressing the time-dependent boundary forcing, which you can evaluate by doing some experiments, in a format that then enforces statistical properties. So I think this is really cool, because this is what's really hard, I think, about trying to use this approach for doing problems where you have actually stochastic forcing. And that's why the recent work, I guess, by your team is really neat, because I have no clue how to do that. Now, there is this question about, okay, let's actually think about using it. What's going to happen? So I'm going to have a boundary condition here. I'm going to actually be moving things around. You're going to have to worry about what the flux is across, right? How are you going to do that? And my intuition is I say, don't worry about it initially. See how bad it is. He was worried, Stefan. But there is the fact that when you use these boundary conditions, most of the electric field is going to keep the stuff away. There will be some, small number that will want to cross. So my attitude is, fine, just reflect them. And Stephen says in lamps, for example, you can also do a what's it called? A soft boundary, I guess. So that might be the way to do it. So you will make wherever you put it, you're going to make an error because you cannot necessarily confine the things that are going on in here from crossing the barrier. But I would argue that the actual flux is going to be really small because most of the force on these particles will be much more accurately calculated because I'm using the whole thing. Does that answer your question?
Yeah, of course I have other questions, but we can discuss that.
Yeah. Okay, so, what? Oh, good. Yeah, so that's basically it. So there's two ways that I could think of, making this sort of insight known. So first of all, again, I want to emphasize what I find interesting, I don't know why the check marks came out, is that, first of all, this way of thinking about how to, even if I'm just doing flow in here, and suppose I just want to do DFT in a box, infinite boundary conditions, this is a way of gluing on infinite boundary conditions, which you might say extends what your work does and company. And to me, also in my mind, because I know that this type of approach using domain decomposition just isn't used much, everybody's interested in overlapping things, explains why, if I'm sure people here have looked at domain decomposition things, so this doesn't look anything like what we do. And the reason is because most people that do domain decomposition don't do it this way, because they don't want to create these operators or think about them so much or do the you have to do work here, right, to get this data. So they don't want to do that. So it's useful for up here, and then it'll be interesting to see if Stefan is right, I hope he is, that given this data, he'll be able to figure out a way to do this, in which case we're just sort of adding to what he already has extra terms that will improve, hopefully, the accuracy of what goes on in the boundary conditions. Okay, so like I said, this is just a summary. The goal is we can do this. And then what are the conclusions? So even though they don't look at all alike, they're completely different because we're solving potential equations and we have to do device level simulation and we try to represent stuff that's complicated far away, there is a similarity, okay? And I would just argue that, there may be ways that you can improve computational precision and efficiency by using methods derived from domain decomposition techniques, but I should put a star because it's not the normal way. On the other hand, many of you may not have looked into the literature. I shouldn't have, because I figured out what I needed to do, but it may be when you're looking for ideas about how to combine solutions. I mean, there are other ways to do things. You overlap stuff, you do an iterative process, whatever. There are lots of different ideas about how to do this, and intuition about what works and what doesn't. So I would just say, add domain decomposition and multiphysics to your searches for solution methods, and you'll see tons and tons of papers. And lastly, I'd like to thank IPAM and all those involved in organizing and running the long program, Jorg, Keith, and Richard, primarily, because they were the main guys. And then, of course, the funding, which is Army Research Office, the Air Force Office of Scientific Research, and indirectly through HR laboratories. Thank you.